Assalamu alaikum wa rahmatullah. We're back with another video lesson. But I wonder, how well have you been practicing lately? And I hope your answer is you've been practicing very well lately. Now, last time on the previous lessons, we talked about the mass spring system. And of course, we said for mass spring system, we said the restoring force, of course, it is the gravitational or the elastic force for the spring, of course. And especially if, let's say, when the spring, if it is suspended, let's say vertically, of course, gravitational force would pull the spring, let's say, or it would extend it in this case, and of course the elastic force would take the mass or the spring back to its equilibrium position. And then after that, we talked about pendulum, yeah? We said in pendulum, of course, the restoring force was there. Of course, it was a component of, let's say, the component of the gravitational force, and it was Fg. By the way, it was the gravitational force, and we said Fg equal to mass times gravitational acceleration times sine theta. That theta, of course, was let's say can also be sine theta, can also be the amplitude for the simple pendulum as well. And then after that, we talked about simple harmonic motion. If you remember, we said if the swinging or the amplitude of this, or the angle of the swinging is less than 15 degrees, of course, it can be called simple harmonic motion. And we said for simple harmonic motion, remember there were three conditions, yeah? We said the restoring force must be directly proportional to the displacement, but in terms of magnitude, in terms of the direction, of course, they were opposite, yeah? If the displacement were, let's say, to the right, the restoring force was to the left. And then after that, we said the pendulum must be swinging about the equilibrium position. And of course, the third one was there must be, what was it? We said it has to be back and forth, yeah? And I hope that was, I've mentioned all the conditions there. And then last time, of course, we talked about the how to calculate the period of a pendulum, yeah? We said in order to calculate the period of a pendulum, we said period equal to, or T for pendulum was equal to what? And of course it was, T was equal to 2 pi, and of course the square root of, remember for pendulum, yeah? We said that is the length of the pendulum divided by the gravitational acceleration there. Very, very good. Now we'll continue, and also remember this. We said if length is, let's say if length is required to find, we can also say that length equal to, or you can use T squared over, let's say 4. You can use this equation to find the length of the pendulum in case if the length was required. Okay, now we'll continue with this. Of course, we have this question for today. It says what? What is the free fall acceleration in a location where the period of 0.85 meter long pendulum, and of course the period is 1.86 here. Okay, so how are we going to do this? Remember, let's zoom in a little bit. Okay, remember this. It says what? Free fall acceleration. If the length of the pendulum is what? Is 0.85. Let's get this rectangle, and we can do this. Stay with me, all right? So what are we? Remember this. We said if you're willing to find the length, okay, we can use T squared over 4, yeah? But if I didn't notice this. Okay, but here, remember, we're given the length, we're given the period. You are been asked to find what? To find the free fall acceleration here. So we can say, of course, T equal to period. Let's make this nicer. T period equal to what? Equal to 2 pi, the square root of what? Of L over gravitational acceleration here. Okay, so of course now, if you're going to like find G here, you'll have to square both sides in order to get rid of the square root. So in this case, we can say T squared. Let's thicken this, the line here. So we can say period squared equal to what? Equal to 4, because 2 squared, that is 4, and then pi squared, we can just write pi squared, and of course is going to be L over gravitational acceleration. Now, can I switch between, let's say, if you use cross multiplication, you can switch the period and of course their location, of course, with the gravity. So we can say gravitational acceleration equals to 4 pi L over what? Over period square in this case. Now all you have to do just write the numbers into the equation, and then you will get the answer there. So let's change the color. So we have 4 pi, by the way, pi squared. 4 pi squared multiplied by, what is the length? The length is 0.850, and then divided by the period squared. The period is 1.86. The whole thing is, or just this number squared, and of course you will get the answer correct. Let's say use your calculator, you will get the answer, which is going to be 9.7 meter per second square. Why? Because it is gravitational acceleration here. Okay, now here we have another question which is very important. A lot of students might struggle on this. Okay, it says what? A certain pendulum clock that works perfectly on Earth is taken to the moon, where gravitation or gravity on the moon, gravitational acceleration is 1.63 meter per second square. If the clock is started at 12 a.m., what will it read after 24 hours have passed on Earth? Okay, now let's do this one. Remember this, the gravitational acceleration on the moon is 1.63. So in order to start with this, let's start with gravitational acceleration. Let's change the color here to black. Gravitational acceleration on the Earth, of course, you do know that that is 9.81 meter per second square. Now gravitational acceleration on the moon, let's say, that is 1.63 meter per second square here. So now the time is, let's say, if we start, let's say after 24 hours, how long will it be passed on the moon, let's say? So of course, if we assume that the time is 12 a.m. on the Earth, okay? That is a.m. On the Earth, okay? If that is the time here, okay, you can call midnight here, what will be the time on the moon? Now, this is very simple, so bear with me, we'll do this hopefully real easy. Now, in order to do this, of course, you do know that, let's say we're comparing the two, yeah? We know that the period on Earth equals to what? Equals to 2 pi, the square root of, remember, it is a pendulum, yeah? So the length divided by gravitational acceleration, that is, remember, gravitational acceleration on Earth. Okay, or of Earth, let's say, and then let's say period on the moon, of course, equal to 2 pi, the square root of the length of the pendulum divided by gravitational acceleration on the moon. Don't forget, on what? On the moon. Now, it is the same pendulum, so of course the length is the same, yeah? What we're trying to find is, you'll have to find the period, yeah? So let's change the color here. All right, so we can say, in order to find this, of course, we'll have to divide the period on the moon divided by the period on Earth, okay? Divide by the Earth. In this case, of course, what will we get? We will get 2 pi for the moon, of course. That is L over gravitational acceleration of the moon, all right, of the moon, divided by what? Divided by 2 pi, that is for Earth, of course, length of the pendulum divided by gravitational acceleration of the Earth here. Now, you do know that these will cancel out, yeah? And of course, this and this will cancel out as well. What will be left here is this. Let's say t on the moon, t on Earth, let's say, equals to the square root of gravitational acceleration of the Earth. Of course, once you take the reciprocal, gravitational acceleration for the Earth will be up, and then gravitational acceleration for the moon would be down below. So now, if you plug in the two numbers here, we can say, so let me write it here. So we can say t on the moon, period on the moon, let's say, or moon's period, let's say, divided by Earth's period here, equal to, now the square root of Earth's gravitational acceleration, that is 9.81, divided by 1 point gravitational acceleration of the Earth, which is 1.63. Once you divide the two, of course, you will get the square root of 6, let's say. So t of the moon, t of Earth equal to the square root of 6 here. Now we can say, if you cross multiply, of course, or you can say this, t of the moon here, let's draw a line here, t of the moon equal to the square root of 6 multiplied by t of the Earth here. What does this mean? Remember, this means that the period on the moon will be bigger or longer by a factor of, or the square root of 6 of the t of the Earth. If you convert this one to digit, of course, or decimal, we can say t on the moon equals to what? Equals to 2.45 times the period of the Earth. Again, what does this number mean? It means that if it takes 1 second for the pendulum clock, let's say, or if the period is 1, let's say, on the Earth, it will take 2.45 times longer than that on the moon. Why? Because the gravitational acceleration is less. So of course that makes the pendulum to swing, let's say, slower, and slower swinging, that means longer time for one complete period over there. So remember this. But now we know this one here, okay? So in national exam questions, of course, you'll have to say the time or period on the moon will be equal to, or you can say it will be longer by the factor of square root of 6, let's say, okay? Remember, it might give you, for example, or tell you less by this factor. That would be incorrect. So it has to be more by this factor. Or the period on the moon would be, let's say, would be less than the period on Earth by a factor of 2.45. That is incorrect. Don't fall for this. Okay, but we can say the time or the period on the moon would be 2.45 longer than the period of the Earth. On the Earth, or you can say the period on the moon will be bigger than the period of on the Earth by a factor of 2.45. Now let's get back to the main question there. Yeah, it says, so now we do know that the period on the moon will be bigger by this factor than of the period of the Earth. So remember this, after 24 hours, so we can say 24-hour, okay, divided by 2.45 in this case. If that is the case, of course, we will get what? We will get 9 hours or 9.8 hours. But 9.8 hours, that means 9 hours plus 0.8 hours, yeah? But you do know that 0.8, if we convert this one to minutes, multiply by 60 minutes, then we can say the final answer is going to be 9 hours and 48 minutes. Okay, so remember this, we can say that the period after 24 hours has passed on the moon, the time will be the time on the moon, or the clock on the moon, will read 9 hours 48 minutes. Because it started at 12 a.m., so of course 9 hours 48 minutes, that will be the time that is that the pendulum clock will read on the moon. You might say, but how is this, for example, possible? Remember this, there's another way to double check with this, yeah? Remember, we said you can convert this. Let me get a calculator. We can say, okay, remember, we said the time, let me use this again. So remember, the time of the moon will be 2.45 times the period of, let's say, on the Earth, correct? Now, watch this. Okay, so, which means that if, for example, like I've mentioned earlier, if it takes one period on the Earth, it will take 2.45 more time to complete one swing, yeah? So another way to double check with this is this. Let's say we know that in 24 hours, how many seconds are in there? 24 hours, yeah? So we can convert 24 hours, 24 multiplied by, let's say, each hour there is 60 minutes, yeah? And each minute there is 60 seconds, yes? Okay, so we can say the total number of seconds on the Earth, the total number of seconds of the Earth in 24 hours will be 86,400 seconds, yeah? But remember, on the moon, all right, let's say that is on Earth, let's say. On what? On Earth. On the moon, remember, okay? And now, it will, in order for this, let's say it will take 2.45 seconds longer than this. And if you do this, that means these are the number of what? The number of ticks, let's say, the number of periods or the number of seconds that we have on Earth, yeah? But if we use the same number, 86,400, let's say, divided by, remember, for each second that happens here, it takes 2.45, let's say, this factor longer than this, yeah? So if you divide this for 86,400 divide by 2.45, you will get, let me redo this, 86,400 divided by 2.45, and of course you will get like the number of seconds that has passed on the moon will be 35,265.3. Of course, we can ignore the 0.3 there. These are the number of the seconds that have passed on the moon. Okay, remember, it takes 2.45 times longer for every second that happens on Earth than on the moon, let's say. So on the moon, it takes more time for one complete swing, yeah? So these are the total number of seconds that have taken place on the moon, yeah? So if you divide this one by 1 hour, let's say, and you know that in 1 hour there is what? There is 3,600 seconds, yeah? So 35,265 divided by 3,600, of course, you will get once again, you'll get 9.8 hours. And once again, 9.8 hours would equal to 9 hours and 48 minutes, okay? So remember this. So we can say the time where the clock will read 9 hours, 48 minutes on the moon. Okay, so I hope that was clear, but remember this. One thing that is very important you need to know is the conversion or the factor between the two. Period on the moon would equal to a factor which is the square root of 6 times the period of what? Period of, let's say, or period on Earth here. That's one. And if you don't want to use the square root of 6, of course, you can use 2.45 instead of this, okay? So whichever is given, just remember that this is what it is. Okay, so now, of course, here's the calculation one more time as well. So we can say the pendulum clock on the moon would read 9 hours and 48 minutes, and of course that is AM as well. Okay, now let's talk about the period of a mass spring system, yeah? So far, we've been talking about the period of a pendulum, yeah? And of course, the period of a pendulum equal to 2 pi the square root of length divided by the gravitational acceleration, yeah? Now, how can we find the period of a mass spring system here? Okay, watch this. Remember, if that is, let's say, the mass spring system, let's say it could be either this or it could be horizontally. Okay, if you want to find the period, like the time for one complete swing, by the way, once it moves back and forth, remember, back and forth, one time moves down, one time length, and then moves up back to the same point, that is one period, yeah? Okay, so the time for one complete oscillation. Or one time goes to the right and then goes to the left and then comes back to its original position. That is, of course, one period. Or you can release it here. It goes all the way to this point and then back to this point here. Of course, that is one full swing. And the time it takes for one full swing or one cycle, that is called period here. So how do you find the period for a mass spring system? And of course, in mass spring system, period here equals to what? Equals to 2 pi, okay, the square root of what? Of mass divided by the spring constant here. Remember this. Now, based on this, we can say the period of a mass spring system depends only on the mass of the, let's say, the mass that is attached, all right, to the spring, and of course the spring constant, or how stiff the spring is. By the way, remember this. We can say, based on this relationship, we can say the period is directly proportional, is what? It is directly proportional to what? To the square root of the mass, not just the mass itself, yeah? So if I say the mass is doubled, what will be the period? In this case, if we double the mass, we can say the period will increase by the square root of 2, not just, let's say, or multiply by 2, yeah? Why? That is because, based on this, we can say this. Take a look here. Let's say if we said if the mass increases by, or if the mass is doubled, watch this. Here is the period, yeah? And of course, it's directly proportional with this. 2 times, if the mass is double, that means 2 times the mass, yeah? But I believe you know this in math, yeah? So for example, if you have something like this, can I write the square root of 2 multiplied by the square root of the mass? Yes, that is correct, yeah? So of course, but here, you know, like whatever the mass is this, that we keep it the same. So we can say the period will increase by a factor of what? By a factor of 2. Later on, we'll also see that. Or perhaps I can tell you this. Watch this. Let me write smaller perhaps. Let's say we said the mass, if the mass increases by a factor of 2, what will happen to the period? We know that, let's say the mass increases from m becomes 2m, yeah? So the period, it is 2 pi, the square root of what? Of mass divided by the spring constant here. So watch this, yeah? We've mentioned earlier that if I have the square root of the mass, or 2 mass, can I write 2 times the square root of the mass? If your answer is yes, then that means you know this concept. So in this case, becomes 2 pi, the square root of 2 mass times k. Remember, can we take the 2 out and put it right here? Yes, we can say the square root of 2 multiplied by 2 pi, the square root of the mass divided by the spring constant. But isn't this equal to, if we consider this to be the period, for example, what will happen to the period? You can call this one period 2. Okay, in this case, of course, we can say the period will change by a factor of the square root of 2 multiplied by period 1 as well, because the whole thing equal to period 1. Whatever the value, we don't care, yeah? When you increase the mass by a factor of 2, of course, the period will increase by the square root of factor by the square root of 2. Don't forget this. What about if we increase the spring constant here? So watch this. In another way, we can say by increasing the mass, by increasing what? By increasing the mass, the period will increase. If the period increases, that means it will take longer time to complete one oscillation, yeah? Or in another way you could say the period gets longer. Okay, now what happens if we increase the spring constant here? And of course, if we increase the spring constant there, okay, now we can say the same thing by this, yeah, but remember this under the fraction. So increasing the spring constant here for the mass spring system, remember this, we can say 1 over whatever the factor of the k that is increased, 1 over k, imagine this is a factor here, multiplied by 2 pi, and of course the square root of what? The square root of, let me write a factor before somebody comes and complains, say this is not accurate. Yeah? We can say, let's say the spring constant increased by 2, okay? So remember, we'll take the square root of, or the 2 out of here, so it becomes 1 over the square root of 2, and here becomes m times or over the square root of this. But you already know that this is equal to 1 period, so if you double the spring constant, then of course the period will decrease by a factor of, let's say the period will change by a factor of 1 over the square root of 2, which in this case the period will decrease. Okay, now, what else? But what about one more thing here? How about if we increase or decrease the amplitude here? If we stretch the spring more or compress it more, do you think that would have any effect on the period of a mass spring system? The answer is no. Okay, I'll repeat. If I increase the amplitude of a mass spring system, will that change or affect the period of a mass spring system? The answer is no. Why? Because there is no amplitude that is mentioned, or no amplitude in the equation, but of course that would affect something different, yeah? And what is that thing? Remember, it would affect the restoring force. You can see that there is no amplitude here, there is no x in here, so it has increasing or decreasing the amplitude would have no effect on the period of a mass spring system. But of course, we know that in the spring system, the restoring force is elastic force, and of course that equals to kx, yeah? So increasing or decreasing this, of course, it will affect the restoring force, but not the amplitude. So make sure that you know this, okay? The period of a mass spring system depends on the mass, all right? That is attached to the spring depends on the spring constant as well. In another way, we can say the heavier the mass, the longer the longer the period, the bigger or the stiffer the spring. Let's say the bigger the value for the k, that means the shorter the period or the faster the oscillation. Okay, or the up and down movement here. Vibration. Okay, so based on this, remember these study tips are very important. It says, according to Hooke's law, the restoring force acting on the mass is determined by the displacement, and of course, of the mass and by the spring constant. We do know that elastic force equal to negative or minus kx. Okay, and then the magnitude of the mass does not affect the restoring force. One thing I didn't mention so far is, we said, if we increase the mass here, it will affect the period. But will increasing the mass affect the restoring force? The answer is no. Very good, because there is no mass in the restoring force equation. Once again, if I increase or decrease the amplitude, will it affect the period? No, but it does affect the elastic force. And then the next one, a heavier mass will make more time, or will take more time to complete one cycle of motion. So we said the period is directly proportional with the square root of the mass, okay? And the greater the spring constant, the shorter the time, or the stiffer the spring, the shorter the time, the shorter the period. And of course, we can say that the period is directly proportional with the 1 over the square root of the k. That's that. And then for number 6, changing the amplitude of the vibration does not affect the period. Remember, changing the amplitude, like increasing or decreasing x or displacement here, will not affect the angular display, will not affect the period. And the reason why is because there is no x into the equation, but that will affect the restoring force. All right, so we've learned this. So this statement is only true, remember, only true for systems and circumstances in which the spring obeys the Hooke's law. And that is, so remember, as long as the spring obeys Hooke's law, that means you're good, you can use the equations, but if not, then it doesn't work. Which of the following does not affect the period of the mass spring system? Remember this. Whenever you've got questions like this, always write down the equation. For both equations, you can say, yeah? But this one says, which one affects what? Which one affects the period of a mass spring system? For the period of a mass spring system, you do know that equal to 2 pi, the square root of what? Of mass over k. Why? Because it says the period of a mass spring system. For mass spring system, we have mass over the spring constant. So the first one says the mass. Which one does not? Yeah. So will the mass affect or not? Because there is a mass, so that means it will affect it, which is incorrect. Yeah. Okay. Spring constant. You see that there is a spring constant into the equation, so of course the spring constant will affect the period. So that means this is incorrect as well. What about C? The amplitude of the vibration, yeah? The amplitude of the vibration, that would be the displacement x. Do you see any x into the inside the equation or in the equation? The answer is no. So the amplitude of the vibration does not affect the period, so we can say this is the correct answer. But let's take a look at the last option as well. It says the mass and the spring constant does not affect the period. Is that true? These are not true because mass and spring constant both affect the period of the mass spring system. Okay, now take a look at the second question. It says mass spring system vibrating with a simple harmonic motion on a smooth horizontal surface. In what form is the energy in the system when the mass is at maximum displacement? Remember, this time the question is about the energy that is stored in the mass spring system. Yeah. So when we have mass spring system and when the mass is stretched, let's say, or the let's say the mass is at maximum displacement, you know that the spring is stretched. Yeah. So we have let's say, what is the type of the energy in the system? We do know that the energy is elastic potential energy, correct? Remember, it is a mass, so not gravitational, and it is horizontal as well. So the only type of energy that we have is elastic potential energy, that is there at maximum. Yeah. What if the question was at minimum, minimum displacement? Yeah. Minimum displacement here. Let's say in this case there wouldn't be like no potential energy or elastic potential energy as well, because minimum potential energy or minimum displacement, or that in another word is going to be zero displacement here, because the spring is not stretched, so there won't be no elastic potential energy. But what if it was, let's say, maximum displacement when it is compressed maximum, let's say, yeah, maximum compression, that would also be elastic potential energy. So is it gravitational potential energy? The answer is no, yeah, because gravitational potential energy, that would be for the pendulum. Is it kinetic energy? Remember, maximum displacement, that is when the spring is stretched but it doesn't move yet, it doesn't go back yet, it just, you know, like being stretched and the spring has been held, yeah, so it doesn't go back, so it is all elastic potential energy, so no kinetic. Okay. And then kinetic energy and elastic potential energy. This part is true, but because of kinetic, we cannot choose this one as well. So the correct answer, or the answer that we're left with, is elastic potential energy. Okay, now, after we've learned about the simple pendulum equation, or the period of simple pendulum and period of, let's say, the mass spring system, now we can, of course, compare the two, or you can say, you know, like their swinging perspective, like contrasting the pendulum and the mass spring system. We do know that the period in pendulum equal to what? Equal to 2 pi, the square root of length over gravitational acceleration, correct? In another word, we can say the period on a pendulum of a pendulum depends on the length and depends on gravitational acceleration. But the period on a mass spring system depends on what? Depends on the mass and the spring constant. And the equation for period of a mass spring system was period of a mass spring system equal to 2 pi times the square root of the mass over the spring constant. So depends on the mass and the spring constant. And in regard of the restoring force in the pendulum, of course, the restoring force was gravitational force, and it was equal to mg sine theta. Don't forget. So the restoring force in a pendulum depends on the mass, depends on the gravitational acceleration, depends on the sine theta, or the amplitude, you can say. While the restoring force in a mass spring system, it depends on what? It depends on the displacement, it depends on the spring constant as well. So the stiffer the spring, we can say, the bigger the restoring force, the bigger the displacement, the bigger the restoring force. But don't forget, remember there was a negative, and this negative, that means the direction of the opposite, or the direction of the restoring force, which is always opposite to the displacement. And then after that, we can say, what will happen if we increase the amplitude for a pendulum? If we increase the amplitude of a pendulum, of course, that would has no effect, or you can say, on the period, yeah? Or the period will stay the same there. But of course, that would increase the inertia, you can say, because there would be, we can say, in order to cover that swing, of course, it has to go a little, or you can say a little bit, what is it? What is the right word for that? Because we can say the restoring force would be bigger. So of course, that means if the amplitude is bigger, so it has to go faster, and faster movement, of course, that means bigger or higher inertia. And of course, like we said, the restoring force will be bigger because the angle theta will be bigger. So mg sine theta, in that case, of course, the force or the restoring force will be bigger. The periods stay the same. Yeah. What about in the mass spring system? What happens if we increase or if the mass of the system increased? Yeah. If we increase the mass, the period will increase. Okay. And if the period increases, what about the restoring force? Will it have any effect on the restoring force? The answer is no. I think I've skipped number 3. Increasing the amplitude would have no effect on the period, don't forget. But of course, it will increase the restoring force, because the restoring force of a pendulum, of course, if that is, for example, let's say if we use gravitational force versus elastic force, mg in this case, the restoring force will get bigger in this case. Okay. I think I switched it up. Remember, if we increase the amplitude x, of course the restoring force will increase, because restoring force equal to negative kx. Forget gravitational or mg here. Okay. Now, what about if the mass of the bob increased of a pendulum? Yeah. If we increase the mass, I believe it would be best if I draw the 2 equations here. So let's say this is for a pendulum here, 2 pi, all right, and this is, let's say, mass spring system. Okay, the period for pendulum would be 2 pi, the square root of L over gravitational acceleration, but the period here is going to be 2 pi, the square root of what? Of mass times the spring constant. Okay, and of course the restoring force here, let's say R for now, that would be gravitational force, and that is mg sine theta. Okay, the restoring force here, it is elastic, okay, which is equal to negative kx. Okay, so once again, increasing or decreasing the length and gravitational acceleration will affect the period. Yeah? Here, increasing or decreasing, let's say, mass or spring constant, of course, it would affect the period there. Okay, increasing the amplitude, of course, would have no effect on the period here, but it would affect the restoring force, because it makes this sine theta bigger. Okay, increasing the amplitude here does not affect the period, but increasing the amplitude, of course, it would affect the restoring force in here. Okay, and we said increasing the amplitude, we've mentioned that. Increasing the angle theta, of course, it will increase the restoring force here as well. Okay, now changing the location, that is something very important. Remember this, in a lot of times in Rosati questions, there were questions like what will happen to the period of, let's say, a mass spring system if we take that to the moon. Remember, whenever it says mass spring system or a pendulum, your first thing need to do is this. Always write the equation, yeah? The equation that we've said, let's go back to this one here. Take a look. This one, if it is a pendulum that we take to the moon, of course it will affect the period because there's gravitational acceleration that would affect the period. But if you go to the mass spring system, there is no gravitational acceleration. So if you want to measure the period of a mass spring system, whether if it is on Earth, on the moon, on any other planets, it would still be the same period. Why? Because there is no gravitational let's say acceleration that is in the equation, or concerns no gravitational acceleration. But remember, for this to be true, all the mass spring system has to be the same mass and the same spring as well. Okay, so we can say for the moon, of course, or the pendulum, if we take it to the moon, of course, then the period will increase, let's say, or it takes longer for one complete swing, let's say. And of course, you can see here the period changes. The period on the moon will be bigger than the period over the Earth by a factor of 2.45. The restoring force, of course, it will change by what? Change by, let's say on Earth, will be 6 times bigger than the restoring force on the moon because we have a stronger or bigger gravitational acceleration there. What about changing the location? Remember, it does not affect, because it does not depend on the gravitational acceleration, so the period stays the same always. T, or period on the moon, will be equal or the same as the period on the Earth. Yeah, and then the restoring force stays the same. Why? Because elastic potential energy or elastic force on the moon is the same as the elastic force on the Earth as well. Once again, because we said there is no gravitational acceleration concern. Remember, for a pendulum here, all the energy that we have is, if we go back to this, take a look. Let's say, let's move this one a little bit higher. If we have a pendulum that swings, for example, yeah? So let's say here's a pendulum that swings, okay? Now here swings back and forth, back and forth. At a point here, we know that all the energy that we have, it is what? It is gravitational potential energy. All the energy that we have, it is gravitational potential energy, okay? All the energy that we have. But if it is a mass spring system, let's say, if it is a mass spring system here, let's say maximum displacement here, if this is x where x is equal to 0, x equal to 0 at this point here, so let's say this is maximum displacement here, and then what is the type of the energy that is in the mass spring system here? Okay, and of course the answer is it is going to be elastic potential energy. So in a pendulum, the type of energy that is stored maximum displacement, it is all gravitational potential energy, but here it is elastic potential energy. Okay, now let's take a look at these two national exam questions or Rosati questions. It says the mass oscillates on the end of a spring. So what do we have? We have a spring. Don't forget, we have a spring here. Okay, it says both on Earth and on the moon. Where is the period the greatest? Yeah, where is the period is the greatest? So remember, we said on the moon, what is the equation for period? On the moon, and by the way, for mass spring system, yeah, that is 2 pi, the square root of what? Of mass over the spring constant. Now, we know that the gravitational acceleration on Earth and on the moon are different, yeah, but is there any gravitational factors here or variables in the equation? No. So if there's no, that means taking a mass spring system from Earth to the moon has no effect on the period. So what would be the answer? It says on the Earth is the greatest, that is incorrect. On the moon, that is incorrect. The same for both on Earth and on the moon, that is the correct one, yeah? What about D? Says cannot be determined from the information, that is also incorrect. So the correct answer will be C here, because there is no gravitational acceleration in the equation. Another question says 3 identical vibrating mass spring system. three. One on Earth, second on Moon, and third one is on the Mars's surface. Which of them have the greater period or greatest period, let's say? Once again, doesn't matter how many mass spring systems you have, yeah? As long as they're all identical, they are not affected by the gravitational acceleration. If they are not affected, that means all their periods will be equal or the same. All are equal, and that is the correct answer here. Okay, now let's take a look at this one here. It says what? Will the period of a vibrating mass spring system on Earth, okay, be different from the period on an identical, it has to be identical so that it has the same mass and the same spring constant, of a mass spring system on the Moon? Why or why not? The answer is, says, will it be different? The answer is no. Why or why not? Okay. The answer is going to be or not going to be different. The period will be the same. That is because the period of mass spring system does not depend on the gravitational acceleration. But of course, one thing will change. You can say that is what? That is the... No, okay. So remember this. We can say the period remains the same because it does not depend on the free fall acceleration. So we can say time or period on Earth would equal to the time or the period on the Moon. That is always true as long as the spring system or mass spring system is identical. Now, we have a question here. This is one of the easy question, very interesting as well. It says, a body of 1,275 kilogram car is supported on a frame by 4 springs. Remember, how many springs do we have? We have 4 springs. Now, 2 people riding the car have a combined mass of 153 kilograms. Yeah, when driven over a pothole in the road, okay, the frame vibrates with the period of what? With the period of 0.840 seconds for the first few seconds. The vibration approximates simple harmonic motion. Find the spring constant of what? Of a single spring. Remember, we have 4 springs. We want to find the spring constant for what? For 1 spring. So how are we going to do this? Remember this. First of all, you need to combine all the mass that we have, yeah? And then try to find out what is the mass on each spring, we can say, yeah? So let's say the total, can we find the total mass here? So we can say total mass, let me change the thickness here. Okay, let's make a little bit thinner. So once again, we can say the total mass, or total what? Total mass. That is going to be the mass of the car plus the mass of what? The mass of the drivers, yeah? Or the, what else do we have? The people that are riding the car. Okay, so we have 1,275, that is kilogram. Remember, this is the mass of the car itself, plus the mass of the riders, let's say, which is 153 kilograms, correct? Now remember, this mass is would be, or this load would be on 4 springs. Yeah? So let's find out what would be the total mass in this case. The total mass is 1,275 plus 153. So the answer is 1,428 kilograms. All right, but remember, these masses, or this mass, is basically applied on 4 springs. Can I find the mass on 1 spring? We'll divide by 4 in this case, yeah? So divide by 4. Why are we dividing by 4? What is the purpose of doing all this? That is 357 would be kilograms on each spring. On what? On each spring. Remember, we're trying to find what? The spring constant. So in order to find the spring constant, I need to find the mass, yeah? Because based on this equation, period equal to 2 pi the square root of what? Of mass over the spring constant, I need the mass, yeah? But we have 4 springs, yeah? You can either use 4, of course, and then total mass divide by 4 springs, or we could have just find the total like I've did, divide by 4. We'll find out how much mass is on each spring. Now I can find the spring constant of one of the springs there, which are all identical, so that'll be the same for all. Okay, so in this case, remember, we're trying to find k here. So can I square both sides to get rid of this square root? Yes. So in this case, it becomes t squared equal to 2 pi squared. That is going to be 4 pi squared, yeah? And then multiplied by mass divided by the Cyprian constant. Now, of course, we'll swap k and t here. So Cyprian constant equals to 4 pi squared multiplied by the mass divided by t squared. And I have, of course, this is the equation that I'll use to find the Cyprian constant. And you do know that I have the mass now, I have the period, I can find the Cyprian constant. So Cyprian constant k equals to 4 pi squared, okay, multiplied by the mass. Remember, the mass on each Cyprian was 357, and that was kilograms divided by the period. The period was 0.84 seconds, yeah? 0.84, but the period is squared, don't forget this, yeah? Use your calculator, you'll find the answer. So let's say 4 pi squared multiplied by the mass, which is 357 divided by 0.840 squared, yeah? So the answer is almost about 20, yeah, or 20,000. So we can say Cyprian constant, it is 19,974. Of course, we can round it up to 20,000, yeah? But what is the unit for Cyprian constant? And of course, that is Newton per meter. So remember this. The Cyprian constant of one Cyprian is 20,000. If I want to find the Cyprian constant of 4 Cyprians, we'll multiply this one by 4. Okay, so this is how you can do this one very simply here. Okay, now, in terms of the next question, I'm afraid that is all the time that we have for this session. Inshallah, we'll continue starting from practice 3C in the next session. So, until then, keep practicing, and I'll see you soon.